Hey there, everyone. So I hope you've all made it in all right. I hope everyone's rolling in well in all our little virtual boxes, and I hope you can see me in the camera really well here. Just want to say hello, first of all. I'm here representing WeCloudData, Data Science Academy in Toronto. Right now, I'm in the UK, though, in rainy.
Hey there, everyone. So I hope you all
apologies, I'm having echo.
I hope everyone's rolling in well in all our little
apologies for that.
boxes, and I hope you can see me in the camera really well here. Just want to say hello, first of all. I'm here representing WeCloudData.
So I should have muted myself there.
In Toronto.
Great. Okay. Well, again, back in our virtual boxes, we also have technical difficulties that exist in the real world. Yeah, like I said, I'm in the UK right now, rainy UK. We're doing well here. I hope you're well in Toronto. It sounds like you guys are doing great in Canada in general. I'll get to the point. I'm here to represent, to talk about why GPUs are important right now in the world, why they came from a kind of fun place, and why that kind of fun place has become such a serious place or an exciting place. And I'm going to start off by giving you guys a little bit of a high-level overview of what graphics cards are, or GPUs, a term that was coined by NVIDIA, right? And we'll have a look at the kind of brief history of that as well. I'll give you a bit more context as to how the whole pipeline works in terms of video games and in terms of actually moving around a world, because I think it will give you that little bit of context to kind of make that leap from the hardware to deep learning, and also to high performance computing and so on and so forth. Like I said, a brief history. We'll look at how it all began, how we made the leap from Doom to games like Crisis and so on. A lot of you actually out there in the world that are gamers might actually already know about how much of a computer killer Crisis. We'll laugh about that later. We'll talk about where we're at in terms of new cores, in terms of new innovations that are starting to, context-specific innovations that are starting to come in. Now we've kind of steeped ourselves in this kind of new deep learning revolution. And then we'll look at RAPIDS and that whole CUDA-X package of libraries that exist now built on top of the CUDA API. And then I'll give you a brief demo, just a quick run through of a project I'm kind of working on, or a kind of investigation into Twitter. A lot of you guys might have actually seen, or used TweePie. Everyone gets started with TweePie, right? But we'll go down that road later, and then I'll see if I can add some bonus stuff in later after that. But yeah, so let's get started. So I've got a nice picture here of the Turing architecture. For those of you who are familiar with NVIDIA graphics cards, there are also AMD graphics cards, but right now we're talking about a CUDA-specific, NVIDIA-specific platform. I'm going to stick with that kind of analogy. The Turing architecture was kind of the next step after Volta, which introduced Tensor Cores, which we'll look at later. But let me just let me bring all of these up, and you can see I've kind of boxed out all my little the little parts of the architecture here. So what we've got on a high level is a bunch of graphics processing clusters, right? For example, for those of you who are familiar with the RTX 2080 graphics cards out there, they've got 6 graphics processing clusters. And we're already starting to see that kind of parallelism. I can never say parallelism. I don't know about you guys, but I'm always stumbling over that. But so we're already looking at parallelism on that kind of that giant cluster state scale there. And like I said, 6 in the RTX 2080. We're looking at 4 here. And this whole unit is basically responsible for a whole pipeline. Let me add the extra bits. So I'm actually going to make my jump. I'm going to make quite a bit of a leap. And I'm going to start off at my polymorph engine here. So if you think about a frame in a video game, what you're seeing is the end result, right? You're seeing the rasterized pixels, you're seeing the shading, you're seeing the vertices have already been filled in, all the culling has happened. We've gotten rid of all of the shapes that we don't need. That starts off with the polymorph engine. So we get instructions into our graphics card, and we grab our vertices and we start shading the primitives and the whole shading and so on. And we make use of these stream multiprocessors, right? And AMD, you hear all these difference, right? But they're actually just all pretty much the same thing. The stream processor is something that AMD usually says. The CUDA core is the NVIDIA marketing speak, right? And generally a shader core is what we generally call it. Simply because they often deal with pixels, right? So down here within our stream multiprocessor, we've got, again, we're talking about, again, that even more granular parallelism here, where we've got a bunch of scalar processors, arithmetic logic units are in there, floating point units, 32-bit single precision registers, which will become important when I'm talking about RAPIDS later, in terms of speed with graphics cards. So we can actually make use of this parallelism. We can smash through all those vertices really quickly, and then send up to our raster engine. And then the raster engine does that culling, gets rid of all those shapes for us, and so on and so forth. And then we end up with our pixelated image on our screen. And then if you think about that analogy, then we've got that happening multiple times in our graphics processing clusters. And we've got our L2 cache with shared memory, which kind of speeds up the whole process for us in terms of being able to communicate between all of our cores, so to speak. And L1 caches also within each streaming multiprocessor. So let's actually look at it a little bit more high level and run away from that kind of parallelism towards something that you guys might understand a bit more visually. And usually I'd ask you guys, but I can't hear you guys. Does anyone know Fallout 4? All the gamers out there might know Fallout 4. Really graphically intensive game. A lot of people actually discovered recently that there's a wireframe mode. So we can actually see the kind of initial stages of what happens as we're walking around this hugely complex world. And again, going back to that analogy of the polymorph engine, what you get with a game, with a scene, is a bunch of vertices, primitives, and often made up of triangles, because triangles are easy to slot together, right? And triangles are very flexible. We can make all kinds of complex shapes and NPCs and buildings and architectures out of them. And the reason why I'm talking about vertices, and the reason that I'm hoping to jump from that kind of those vectors to deep learning, is think about what's happening in the polymorph engine, right? When you're moving around the world. So you're moving around the world, you're pressing your up and down key and so on and so forth. And you've got all these vertices right in front of you, all connected together in all these primitives. Well, we're actually going to want to translate those primitives to another coordinate, right? So the way we do that is with a transformation matrix, with translation. Matrix multiplication, right? The GPU architecture is SIMD, isn't it? Single instruction, multiple data. So we do a lot of the same thing on a parallel scale. And translation is a perfect example of that. We're moving a whole lot of vertices in a really complex, sometimes nowadays we're looking at 4K games, right? And some people are talking about 8K games being a possibility with the new graphics cards that are coming out now. We're doing a lot of translation, so we're doing a lot of similar operations in one go. I've got an example here of a sphere. Think about all these vertices moving in a direction, translating in a direction. And then you start to think of the scale and the kind of context-specific hardware that the graphics card is. Let me move on to that. So then we make the leap and think about deep learning. What's deep learning? Deep learning isn't just matrix math, right? But a lot of it is, or a big chunk of it is, you're talking about weighted inputs, right? We're talking about tuning weights. We're talking about those of you that actually started off in the gaming sphere and made the leap into deep learning will actually be comfortable with convolutional neural networks, where we're convolving images and we're looking for edges with Sobel filters. And the graphics card is perfect for that kind of operation, for that kind of parallel matrix math, right? And so we're starting to go from that kind of high-level view of a game down to these kind of complex mathematical structures. The graphics card is a good kind of workhorse for this kind of operation. So I'm going to actually jump back a little bit to the history of it. Anyone remember Quake? I know I'm saying this without the two-way mirror of you guys being able to speak to me. I'm just going to grab some water. But Quake was really important. Everyone always talks about Doom, right? Doom was great. This 3D realized world, and people always talk about Duke Nukem as well. This 3D realized world you could just knock around, this whole world to explore. The thing about Quake, the thing that was so complex about Quake at the time in 1997, and I remember playing it and having my mind blown as a little kid, is you could look up and you could look down and you could look left and right at the same time. You had a whole world view. You could actually explore an entire world. And that was really graphic. That was really intensive. And at the time, you had like software renderers specific to Quake and to Half-Life, and all these innovative games that would do that work for you. And not to mention at the time, really complex texture models and NPCs. Polygons are starting to get more complex. Let me take the... And then we started seeing the emergence of very contextual, specific hardware, like, for those of you who already know the history of this, the NVIDIA GeForce 256. And that's where the term graphics processing unit was coined. We start to see the dawn of this new age of complex games, and we start to see games like Crysis, a running joke in the gaming world, the rig melter, the desktop melter. This is actually the remastered version now. But back in the days, this would destroy your computer if you didn't fork out for a good graphics card. Simply because of those reasons we were talking, think about it on that low level again. Every time you play a game, think about it. All these vertices moving, translating, and then the raster to do the work of translating that into a 2D pixel space. Really quite amazing what games do in real time now. Nowadays, we've actually moved from Crysis and the rig melting to these new kind of innovations, very specific cores now, instead of just having scalar processors now. And this is very NVIDIA specific. We have things like Tensor Cores that are fused operations. Fused matrix multiply accumulation. So we get mixed precision, single point, and a double precision operations. So we can basically, and these are obviously very deep learning specific as well, because we can start breaking down our operations. We can start breaking down our matrix multipliers and accumulations into chunks. And the speed up is incredible. For those of you who are lucky to have it started off with the Volta architecture, and I think we're in the 3rd generation A100 Tensor Cores. We'll have a look at those a little bit more in a second. And now we've also jumped to very specific cores like the RT core that you see in RTX graphics cards now. Most it's not, you don't need an RT core to have ray tracing, but this speeds up the process by having a dedicated pipeline. There's a whole process of having to scan these volumes for the polygons that you need at that triangle intersection to shade it. That's dedicated in an RT core, and then you get these really crazy real-world physics, these real-world, real-time lighting that we're going to see in games like Cyberpunk 2077 soon, which will hopefully be that dawn of that kind of next-gen ray tracing. So yeah, exciting times. I'm excited to see what's next, what kind of crazy cores people are going to invent next. Let's actually start moving towards rapids and start thinking about that. So like I said, Volta architecture. We started off with a Tensor Core, right? Tesla V100s, at the time a behemoth of a data center graphics card. Really, really powerful. For those of you who have Colab Pro, you'll have access to those and you'll see how fast those are. The Ampere A100 as well, which is able to partition its GPU into separate instances for multiple users. An incredible technology, very exciting, and the kind of new generation of Tensor Cores are involved there. And rumor has it, I don't know whether anyone can throw up in the chat whether they know more about it, but we're talking about, the code name is Hopper, right? There's so we're talking about a multi-chip situation where multiple dies. The implications of that, I don't know yet. We need to see that graphics card and whether that's even real. But the innovations are happening, and I'm excited to see what those are about. So we've talked about the hardware. And in 2006, we started to go from started going from leveraging that context-specific hardware to building APIs like CUDA in 2006, the world's first general computing platform for high-performance computing and for artificial intelligence, and for generally leveraging the parallelism of that hardware. And then right on its heels, we have Opencl, an open platform. Is it the Kronos group? Maybe someone can correct me there. Developed by these guys. So we're starting to see kind of competition and so on and so forth. But like I said, I'm going to stick with the NVIDIA platform for obvious reasons with Rapids. And then moving towards Rapids, we have the CUDA X collection of libraries that are Tensor Core optimized. I don't know whether you need Pascal onwards. You need Pascal onwards for Rapids, but I'd imagine that's the case with a Tensor Core optimized suite of libraries. And we're talking about AI and HPC. We're talking about libraries cuBLAS for linear algebra and sparse linear algebra specific libraries and simulation libraries. We're starting to see really cool speed ups in our scientific computation. So we're moving from that age of leveraging that technology to actually working into our own context now. And now we have Rapids. And Rapids is really quite new, and there's lots of bleeding edge versions getting pushed all the time. So I am having trouble keeping up with all the new innovations and so on. But what I'm going to look at in this session is CUDF, or CUDF, which is kind of like a pandas-like API. Some of the functionality is missing still, especially with string operations, and we'll kind of talk about that. but the speed up is incredible, and that's what's important right now, and I'll discuss that in a second. And I'm also going to discuss a little bit, or we're going to look at a demo of QML, the machine learning library, which is kind of an analog to sklearn, and that's where we're really seeing the speed ups. You'll find that jumping, bridging to pandas is kind of time consuming, and we'll see that in a second. But QML is where it really shines for me. So let me jump over to the next. Oh, actually, no. I'm just going to go jumping around there. Also, Dask integration. So right now with Rapids, if you have a multi-GPU cluster available to you, you can start spreading and distributing your workload, which is incredibly exciting if you're lucky to have the resources to do that. But we'll have a look at that in a little bit as well. It's worth noting, and I'm just going to pause for a little bit of water a second, guys, that this is a Linux platform. It's so it requires a Linux host, but that in itself is a very kind of flexible concept. So we can have a hosted IPython environment, or we can use Conda, or we can build from source, or there are kind of Dockerized versions that are kind of ready to go. Google Collaboratory right now, so Google Collaboratory right now is stuck on version 0.14. And I'm going to go through this menial stuff with you guys because it kind of saves you a lot of time banging your head, which I did when I first went down this road. And the reason why they're staying with 0.14 is because I believe Collaboratory is sticking with Python 3.6 for now. So they can't move on to version 0.15 because I believe it requires Python 3.7 or 3.8 onwards. It also requires an installation script, which we'll see in a second. I've got all 3 versions running for you guys. So there's a little bit of time involved setting up without that kind of persistence in Colab. But you do get access to KAs in Colab, right, for free. Sorry, there's basketball popping up there. I don't know who's a basketball fan out there, but the Miami Heat are in the finals, and I'm excited about it. So I got all the news popping up all the time. So you get access to Tesla KAs, which is great for a free hosted environment, right? But then if you fork out that little bit extra for Pro, you're going to get a V100 like we were talking about with those incredible Tensor Cores. Blazing SQL is something that's coming about as well. And the great thing about Blazing SQL notebooks is it's pre-installed. It's built to push raw data to a Rapids environment. That's the idea. And I've just been informed recently that they're actually going to start bringing in multi-GPU clusters as well, which is super exciting. Being able to use multi-GPU clusters and Rapids will just be just blazing fast, hence the blazing SQL, right? And they have Tesla T4s. So keep an eye out for that. Have a look at that. Those are available to you on the Rapids site, all the links and so on and so forth. So let's move on to the next part. And then in terms of a local machine, you're going to be mucking around with Linux or anything knows that, the 1604 Ubuntu and 1804 is starting to become the kind of stable release for everything. You'll find that's the back end to a lot of stuff now. And CentOS as well. And like I said earlier, it's Pascal architecture onwards. Again, I think it's because of the Tensor Core optimization. And just to reiterate, those Tensor Cores with those fused operations are really important innovation with this kind of work. I'm going to say enjoy the conference, but we're not done yet. We're going to actually delve into our demo. So I have everything up for you. I have all the versions, if you bear me 1 second. So just a quick look. I'm actually going to use Collaboratory in this situation, but we've got the great thing about Blazing SQL is you can look at your GPU resources a lot like Dask, right? We can see what's going on as we go. Everything's set up, ready to go for you. There's nothing to worry about. I've also got a local setup. We might have time to look at that later, but let's jump into our collaboratory session if I can find it. Bear with me 1 second. Sorry about the gap there, guys. There's always a technical difficulty, isn't there? Aha! Great. Cool. I hope you guys can still hear me and see my screen and so on and so forth. So here we've got our environment. I encourage you guys to. The reason why I showed you those initial 2 platforms is because they're free right now, and I encourage you guys to investigate those in the sense that they're available to you. And my assumption is that not everybody has a local Linux machine, right? You might be able to dual boot or triple boot or whatever you want to do, but this kind of gives you that that input, that kind of that doorway into the Linux world. So do check out Colab. Do check out Blazing SQL. Just to give you a little bit of background into what I'm doing here. And if I jump back to this screen, sorry about jumping around there, guys. You see, I've got a bot-o-meter up here. I'm looking at Twitter, and I was looking at the information that was coming in from TweePie, and I started noticing some interesting things about total statuses per day. And I kind of wanted to do a bit of detective work about it. There was something that was kind of confusing me, and it still does kind of confuse me. And I want to show you that. So to give you a bit of context, I have TweePie running just constantly 24/7. Obviously with timeouts being dealt with in a GCP Google Cloud Platform virtual machine. And then I'm pushing the CSV to a bucket, Google Cloud Platform storage bucket. I was hoping to do stuff in real time, but the CSVs were getting massive, and I thought that might be a good opportunity for me to start to leverage RAPIDS to use that kind of massive data. So what I've got here, this is already installed, and what you guys will want to do, and it'll tell me that my destination path is already already exists because I've actually already installed this ahead of the game to try and ward off any technical difficulties that might happen. If you have a look at the RAPIDS site, for those of you who are still who don't know anything about RAPIDS and are starting right from the beginning, I got all excited because I misread the information and I thought 0.15 was stabled on Colab. That's not the case, so ignore this. It's still 0.14 for that reason. But if you go on their site, there'll be a link to a Colab notebook that's ready to go for you with the installation script ready to go. It's a matter of just going through the process. I've added some extra things for speeding up transfer for my G-Cloud bucket. I've added a bit of Dask ML, and the reason for that is just for grid search cross validation, which we'll hear. And Dask CUDA, I'm not actually going to show you because I'd need a bunch of graphics cards to do that, multiple graphics cards, but we'll have a look at the kind of API there. So I'm installed. And I've got my CSV pushed over from my my bucket, and it's pretty big. It's 7 gigabytes, and it was originally like 10 gigabytes, but there was some problematic information in there, and I'm not sure what it was. I still need to investigate. So I split into chunks, and then I put it back together again. And now, which is why it's called Winner Winner, because I was excited that I got to a point that worked for me. And I've already, give me 1 second. I've already grabbed my CSV, and my CSV is loaded as a cuDF data frame, GPU optimized data frame. Now, something I really want to hammer home for you guys, because it's something that you'll probably bang your head with also when you're going through this process, is to look at the set allocator and start off initially. And I'm still trying to figure out all the different kind of parameters here, but start off with your cuDF set allocator as managed. What this does is it kind of automatically manages oversubscription on your graphics card. So I can actually show you what I mean by that now. Those of you who deal with graphics cards a lot know this command fully well. And you can see I'm already relieved, because no technical difficulties, because I know that in my my VRAM I've got my data frame loaded, and we can see that a chunk of the Tesla V100's RAM which is 16, is already populated. Now, like going back to this cuDF set allocator, what this does is, if I didn't have this on, there's something about loading. I'm not quite sure yet. I'm doing that investigation. There's something about loading a large data frame. There's a kind of memory fluctuation that just crashes the whole thing. Manage sorts that out for you. It deals with that kind of oversubscription between the host and the device. And that, if there's one thing you're going to take away from this, in terms of taking your first foray into Rapids, it's this. I think you remember this, because it's going to save you a lot of headache. Also, I'm using Colab forms here just to knock around between all my CSVs. Like I said, I've already grabbed my CSV, which is Tweet's latest, Winner Winner. But what I'm able to do here is I'm able to switch between my my Rapids API and my Pandas API if I wanted to debug or do any work like chunking that I can't do necessarily with Rapids right now. And then I've actually forgot to drop the index for those of you who have done that before. So I got rid of that. And what I ended up with is all of this information here. And I'm going to keep giving you context, because I think it's really important to what I'm saying here. What I've done is I've taken a subset of Twitter, the politics hashtag. For those of you who are familiar with TweetPie, you can take those hashtag-based subsets. You can do keyword searches, right? And you can do it. And what I'm doing is I'm grabbing this information in real time, because I wanted to see what was happening right on the edge of right in the event of Twitter, whether there was something really interesting happening. And there is something really interesting happening. And I've got a lot of information here, and a lot of this information I'm going to get rid of, because I need it to be numeric, and I need it to be single precision, right, to get that graphics card speed up. So originally I got really excited. I grabbed friends, followers, but then I also got the author-based connection. So if someone tweeted or retweeted something, I wanted to grab all the information about the author that was being retweeted to see if I can find some kind of pseudo data science sociological connection between tweeting and so on and so forth. So that's why I have so many columns there. I'm grabbing a quick value counts here. And you can see there's a lot of tweets involved. If you give me 1 second. Yeah, you can see the top retweets, 33,000 about public health decisions. So, you know, these tweets are going to get pretty incendiary, just as a disclaimer to you guys. So apologies about that. And again, another way of checking I can't stress enough how important it is to constantly be checking your memory usage. PyNVML is a great way of doing that. So always check your memory usage. Make sure you're not going to crash. Here's the QDF Dask API, and again, we're not going to use it. What it does is it kind of deals with it in chunks. But do check out Dask, but we're going to move frankly. And now I'm going to get to the crux of the context of what I'm talking about. What I realized in total statuses. Now, if you think about total statuses, what it means, my understanding is it means tweets, retweets, basically all action in Twitter, right? Now, if you look at, I was hoping to get I couldn't find a Canadian politician in there. Sorry, guys. So I ended up going for Kamala Harris. But if you look at Kamala Harris's Twitter, and bear me 1 second, and again, it's going to be pretty incendiary because of the politics as it is right now. But if you look here, 14 points. And then if you look at her, what we're seeing here is every time she tweets, I'm just grabbing, or retweets, I'm just grabbing the total statuses. It's pretty similar, 14.7K. This is a CSV from a couple of months ago. So there's nothing really weird happening there. So what I ended up doing was a bit of feature engineering. And I wanted to grab the total statuses on average per day. Now, because something that doesn't exist right now in QDF is the apply function for Pandas, which a lot of you guys that already know the Pandas API use a lot, right? But you can actually do something really simple and just bridge the Pandas. Here, I can then I can subtract my days, and then I can get my average status count. Because what I wanted to do was then filter, because for bots, right? I wanted to check each description, and I wanted to check each tweet for any obvious bots, like things that say chat bot, because a lot of bots just reveal themselves, right? They don't mind. They're not doing anything insidious. They're research bots. So I wanted to grab a little kind of subset. But then I had a little hunch that there's something going on with total statuses. So I grabbed for those of you who know Twitter really well, I believe the total statuses per day cap is like 2,000, but I ended up going for 20,000 to see people that are really, or bots that are really breaking that limit. And then I plotted it. And take a look at this. What I'm not sure what this means, but some of the average status counts for a day are up in the 1 million. I don't know whether that's spamming or I'm not actually too sure what that means. But so I wanted to investigate further. So if you have a look at every single one of these are banned. So I'm onto something here. I may not fully know how to interpret the 1.2 million or the 1.1 million attempts, but I know there's a pattern here. So what I ended up doing was declaring all these bots. And then on top of that, what I ended up doing was grabbing all the verified accounts, all the accounts in there in the backend that has the Boolean verified as true. So I grabbed all those because I know for certain that they're not bots. They're people that are being verified. They're official accounts. They're accounts that Twitter are okay with. I might actually be wrong. They might actually be verified bots for reasons that we were talking about earlier. But that's the data I ended up with then. And then check this out. So I checked for my average status count over the threshold again, and nothing turned up. So there is some kind of connection there. It seems that bots or people that are getting suspended are trying to attempt to push over that status limit. Again, someone could correct me if that's the case, but there seems to be something going on there. So with a bit of feature engineering, I end up with a bot or not data set. So is bot 1 or 0? And then I wanted to leverage RAPIDS to help me figure that out. So let me check how many I've got in my. Give me 1 second, guys. I realize I've done a lot of talking, and now there's. I'm gonna have to run through all these again. Now might be a good chance for questions if anyone. While my computer's slowing down. Okay, that's okay. So it seems like my computer's having problems here. Apologies for that. So what I'm going to do is I'm going to avoid the lag, and I'm going to jump on like a true professional, and I'm just going to tell you what happened. So apologies for that. Great. So what ended up happening was I ended up with all this information, right? And I know I want to get rid of a bunch of it, but I know I want to head down that investigative road of status counts. And I want to see if there's some kind of feature importance with friends and followers. Because we've all got that inkling that maybe, you know, people have that hunch that, you know, bots are bots and you're not going to follow them, right? So what I ended up doing is sorting my data by filtering the authors out and filtering the original author's ID out. Then I grabbed all my numeric D types, and then I ended up with this. But it's not good enough, right? Because they're all in they're all float 64 still. They're all still double precision, and I'm not going to get that graphics card speed up. So then my next bit of feature engineering or pre-processing is to grab all those D types that are in 64 and float 64 and convert those all to float 32, which gives me what I want. Cool. Okay, so we can run these cells. That's cool. So what I really want to show you now, and I've obviously dropped my ground truths as well, and I'm really locking up again. I'm really sorry for this, guys. Didn't have these kind of difficulties. Down to the bottom here. And I'm hopefully going to show you that. So what I wanted to do is I wanted to smash this all through I wanted to figure out how fast the QML random forest classifier is. The way I'm going to do this is just time both, right? So 726 ms, and I can pickle that. I can get my prediction. Not bad. Now, if I run it through sklearn, for those of you who are familiar with, oh, sorry, I've interrupted my keyboard. It's going to take a lot longer. There's a lot of information that we're dealing with here. So you can already see the vast speed up that we're getting from leveraging the graphics card here. Once things start getting smoother, once we all start figuring out how Rapids works, and once those bleeding edge versions start adding more and more features, we're going to be classifying left, right, and center super speedy. And I'm really excited about where this is taking us. It's still taking. Last time I did this, it took about a minute, but I'm going to keep talking through it, and hopefully, yeah. Having a little struggle. Another thing that you guys can do, thankfully, with QML is also a bit of grid search. So we can find a bit of parameter tuning. I'll have a look at that. Again, sorry for my laggy screen there, guys. I'll try shutting some of these windows. Cool, yeah, so about a minute there. So that's a massive speed up. That's incredible, right? And again, go all the way back conceptually to the parallel architecture there. We've gone from Quake and Doom all the way to that. Just incredible. Two things that we can and can't do are, I can get my accuracy from sklearn. I can also plot feature importance. It doesn't exist yet with, as far as I'm aware, maybe someone could correct me with the new bleeding edge versions, the nightlies that are coming in now. But I don't believe feature importance is included in QML right now. I may be very wrong with that. It's happening so quick now. But you can see that followers are important. Like we thought there might be a link there, and it seems to be a link there. And like I said, we can leverage Dask ML though with grid search, and we can do a bit of parameter tuning, and we can grab our appropriate number of estimators or max depth. Bear with me 1 second. Oh, I deleted it. So if you bear me 1 second. I was actually running through every single possibility a few months, about a month ago. And so I was having to delete a lot of variables from my memory. There was a lot going on. So we can run a quick grid search and get and grab our best parameters for our number of estimators and max depth, which is great. So we're getting somewhere. So that's a lot to work with Rapids, even though they're still kind of pushing through a lot of features. There's a lot that we can do. What I'm not going to show you is cosine similarity, because it needs to run on my local setup, because it's the 0.515 bleeding edge nightly version, which actually does work obviously on, bear in mind, on Blazing SQL. I just haven't had a chance to kind of port it over yet. I'm working on all these different platforms. But cosine similarity, I can tell you, is super fast. So we can create TF-IDF matrices, and we can search right through our tweets in literal seconds, through all of the tweets. Do I have a version of it? So you can see I've put someone else's tweet up here that's pretty badly spelt, and then I've got all my similar tweets out of millions, tens of millions of tweets in blazing fast in no time. So it's worth going down that road. And I believe Rapids also have some example notebooks for how to use Cosine Similarity, and I believe they've actually cleaned it up and sped it up for 0.15. So do go down that road. So what I'm actually going to do is I'm just going to reiterate once we've had it. And sorry for the jumping around. Where was I? So you see we're still doing our grid search. We're going through quite a lot of stuff there. The few things I want to reiterate for you guys in the last 9 minutes is, for those of you who are visual thinkers, always think about that architecture. Always think about games. I think games really help me think about how deep learning or high performance computing or GPU enabled data science works. Just think about matrix math. Think about those registers. Think about all the innovations that are happening right now. So remember those set allocators. Remember right at the top. In fact, I'm not going to jump around and confuse you guys, but remember the, I forget I'm on the screen sometimes. Remember set allocator. Remember oversubscription is really important. You don't want to be banging your head with that. Also remember that if you look at the kind of people that deal with strings a lot, there's still a lot of functionality that's missing. So do remember that 2 pandas is your bridge that's going to help you get that functionality that you need. Actually, going back to the filter that I had up here. You'll notice that a lot of string contains actually the kind of string API functionality actually works in QDF right now, Rapids in general. Strings have come a long way. But these flags don't, which is why we need to bridge to pandas. If you wanted something case sensitive as well, you would also need to bridge to pandas. Or if you wanted to deal with missing values, you would also need to bridge to pandas. So do bear that in mind when you're dealing with this library. What else to think of? Bear in mind that it's also Linux, and also bear in mind that there are those other opportunities for you to take that leap into a Linux environment if you need to. And I'll probably leave it at that and ask for questions, because otherwise we're taking a leap into another laggy situation. But I hope you guys enjoyed yourself, and I hope you guys are going to enjoy the conference, and I'm looking forward to seeing the rest of it. I will be around for a chunk of the day, so you can feel free to send me questions on LinkedIn or DM me if you want to do it in your own time, and I'll happily kind of investigate some of these problems with you or just point you in the right direction. And yeah, conference time. Sorry, go ahead.
Rhys, we actually have a couple of questions that came in. It would be great just to squeeze them in there before we end the session. The first one that is, says, do I need GPU for machine learning?
You don't need a GPU. As we saw right here, so going back here, and again, apologies guys for jumping around. My computer seems to have sorted its life out now, but oh, sorry. But my finger hasn't, and I pressed the space button, so I'll get to it as quickly as I can. You don't need a GPU for machine learning necessarily. sklearn you can just do on the CPU as we were showing here. So what this was a compare and contrast between a library that's an analog to sklearn on a GPU using single precision. With a library that's on a CPU? So that's a great question, and it's given me a chance to kind of to reiterate that. Something that is happening right now is CPU-based parallelism. You've got all kinds of crazy CPUs now, like 32-core Threadrippers and so on, and Dask helps you do that. And there are lots of other libraries for parallelizing your pipeline. So no is the answer, but if you wanted to speed up, say, deep learning, which involves tuning a lot of weights and so on, you probably need a graphics card. Does that answer the question?
Yeah, definitely. Thanks for clarifying that. And then another question that came in is, are there alternatives to RAPIDS that are worth looking into as well?
In terms of GPU-based, well, I guess what I was just saying, there's Dask in terms of leveraging the CPU and leveraging the GPU. So do look into Dask. There are things like Panda. I always have trouble with the parallel, but it's called Pandarallel. There's a lot of little libraries that are competing with each other. So Pandarallel, Dask. You can also go down the big data kind of road as well if you wanted. I believe there's rumors of getting more functionality with all the kind of Apache libraries and so on, because this is based on kind of similar functionality. But yeah, there's a lot. It's worth looking in that direction because it isn't just RAPIDS. But RAPIDS being so close to NVIDIA and so close to those innovations, you're going to get people who really know what they're talking about in terms of the CUDA API and getting those kind of fine speed ups.
Cool. And the last but not least, definitely question, because I guess the person is looking for maybe a use case or an example. The question says, what industries could really benefit from using GPU analytics or RAPIDS? Can you give us examples?
Anything that's kind of, think about Pandas is anything that's tabular. Whatever you want to use it for, anything that's kind of investigative. You can have GPU accelerated analytics. Whatever you put your mind to, really. Like I said, a little bit of the functionality is missing, but it really depends on kind of where you're putting your imagination here. And there's also, it's worth bearing in mind, there's XGBoost functionality starting to kind of draw in as well. So you've got those kind of catch-all machine learning algorithms that can be applied to a lot of classification problems that can be in terms of, credit anomaly or spam filters or wherever you want to put it. That's the great thing about where we're at right now. It's I could spend all day listing the industries for you.
Awesome.
I hope that's not too vague.
No, but it's cool. So it basically could be applied to any industry and any company of any size. Yeah,
RAPIDS is giving you the foundation here for really fast insight and analytics. I think is a good place to start. And right now we have access to these kind of notebooks like Collaborative, but we also have access to really massively scalable notebooks like AI notebooks with Colab, or you've got Azure and stuff. I'm not sure about the compatibility right now, but yeah, anything analytics based, anything with a bit of detective work, RAPIDS is going to get that speed up for you.
Great. Well, Rhys, thank you so much for such a fantastic presentation and workshop. Yeah, I hope you get to stick around a little bit. If people want to reach out to you directly, that would be amazing. And I hope you get to enjoy the rest of the show.
Great. It's great speaking to you all. It's great being here. And like I said, enjoy the conference and throw me some questions if you have them. And I'll try to answer that the RAPIDS in terms of industry question in more context to whoever wants a kind of further answer or further embellishments on that. And yeah, great to see you.
Awesome. Thank you.
No problem.